Okay. Hi, everyone. I'm very excited to be here. Yay! Okay, so I'm Hanna. I'm a senior researcher at Microsoft and an adjunct associate professor at UMass Amherst. And today I'm going to be talking about machine learning for social science. And to prepare for this talk, I watched a whole bunch of SciPy keynotes. And roughly speaking, I think they belong to two groups. There's those that are about sort of SciPy and Python itself, and those that are about awesome things that people have done and implemented using the SciPy stack. And just so we're all on the same page, mine is in the latter category. Okay, good. So I've been using Python for about 6 years now. Like many old school machine learning researchers, I've programmed in a ton of different languages over the course of my research career. I started out using MATLAB, and as a free software advocate and a Debian developer, this made me really, really sad, but it was just kind of what you had to do back then. I then spent several years shifting from pure MATLAB, which was too slow, to MATLAB plus C and C++, then to pure C++, and then finally to Java. However, when I became a professor, suddenly I had no time, and the overhead of writing Java became prohibitive. So I started playing around with Python, and that's kind of when everything changed. Interactive mode removed all of that overhead, and suddenly I was able to incrementally prototype my ideas really quickly. And then once Python came along, it was really easy to speed up the slowest bits of code, sometimes by orders of magnitude. And that's where I'm at nowadays. I'm pretty happy with it. It's working out pretty well for me. I really like Python much more than any other language I've ever programmed in, so that's great. But like I said, this talk isn't about Python or SciPy as such. There are plenty of people in this room who can tell you much more about those things than I can. So what I'm going to do is I'm instead going to tell you about some of the things that my students, my collaborators, and I have actually done using Python. Great. So, although I'm a machine learning researcher by training, much of my recent work has been in the emerging area of computational social science. So the study of social phenomena using digitized information and computational and statistical methods. So for example, imagine you want to know how much activity on websites such as Amazon or Netflix is caused by recommendations versus various other factors. To answer this question, you might develop a new statistical model for estimating causal effects from observational data, such as the numbers of recommendation-based visits and the total numbers of visits to various different product pages over time. Alternatively, imagine you're interested in explaining when and why lawmakers' voting patterns deviate from what would be expected from their particular party affiliations and ideological positions. So to answer this question, you might model a set of sort of issue-based adjustments to each lawmaker's ideological position using their congressional votes and the corresponding bill text. And finally, imagine you want to study the faculty hiring system to determine whether there's any evidence of a social hierarchy reflective of inequalities in social status rather than just scholastic merit. So here you might model the dynamics of the relationships between universities, so who's taking jobs at which other schools, and then use this model to analyze the placements of thousands of tenure-track faculty. So unsurprisingly, tackling questions like these requires an interdisciplinary approach. And for me, this shift in direction has really given me an opportunity to start thinking outside the algorithmic black boxes that are often embraced by the machine learning community, and to instead focus on the opportunities and challenges involved in developing machine learning methods to analyze real-world data about society. So I thought I'd start by talking about that, focusing on one of the biggest differences between computer science and the social sciences, and its implications then for computational social science. So When I first started working in computational social science, I kept overhearing conversations between computer scientists and social scientists that involved questions like, I don't get it, why is that even research? And I couldn't work out why. This seemed like a problem. But then I found this quote that I think really captures the heart of this disconnect. Computer scientists may be interested in finding the needle in the haystack, such as the right web page to display from a search. But social scientists are more commonly interested in characterizing the haystack. So in other words, the goals typically pursued by computer scientists and social scientists fall into two different categories. The first is prediction. So prediction is all about using observed data to reason about missing information or future yet to be observed data. And these are finding the needle tasks. In general, it's computer scientists and decision makers who are most interested in them. And unsurprisingly, machine learning has been traditionally dominated by prediction tasks, such as classifying images or recognizing handwriting, or even playing games like chess and Go. The second category is explanation. So here the focus is on why questions. In other words, finding plausible explanations for observed data. These explanations can then be compared with established theories or previous findings, or even used to generate new theories. Explanation tasks are therefore characterizing the haystack tasks, and in general, it's social scientists who are most interested in them. For example, what is the role of gender in the workplace? Are government organizations more likely to comply with public records requests if they know that their peers have already complied? Or how is crowd work changing the employment landscape? So, perhaps unsurprisingly, these different goals, prediction and explanation, lead to very different statistical modeling approaches. In most prediction tasks, causality plays no role. The emphasis is firmly on accuracy. In other words, we don't care why a model makes good predictions, we just care that it does. As a result, models for prediction do not need to be interpretable. This means that there are few constraints on their structure, and they can be complex black boxes that require large amounts of data to train. In contrast, explanation tasks are fundamentally concerned with causality. Here, the goal is to use observed data to provide evidence in support or opposition of causal explanations. So as a result, models for explanation must be interpretable, and their structure must be easily linked back to the explanation of interest and grounded in existing theoretical knowledge about the world. Of course, since association does not imply causation per se, explanatory modeling does not constitute causal explanation in and of itself. Rather, the underlying social theory provides the causality, while the statistical model applied through the lens of that theory is used to test hypotheses about the theorized causal explanation. And then these findings can then be used to revise the theory as appropriate. So when social scientists develop models for explanation, they usually specify them in terms of variables that represent theoretical constructs. So these are abstractions that describe some phenomenon of theoretical interest. Some of these constructs, like those on the left of this slide, can be directly observed. So for example, I really can go and measure somebody's height or record what they eat for lunch. But other constructs can't be directly observed. I can't just go measure influence or status in the same kind of way that I can measure level of education or voting history. But social scientists still want to reason about these unobservable constructs. They still want to include measurements of them in their explanatory models. So therefore, they need some way of measuring them. For example, many political scientists are interested in theories involving senators' ideological positions. Although these positions do not manifest themselves directly in the world, they do have an effect on other observable constructs, such as senators' voting patterns. Political scientists have therefore developed a variety of statistical models to infer or measure ideological positions from observed data. So models like this are known as measurement models. And this is actually where my own research fits into computational social science. I draw on ideas from computer science and statistics to develop new measurement models for social scientists. It sounds really boring, but it's seriously not. It's kind of awesome. And over the next 20 minutes or so, I'm going to tell you about two related measurement models. The first is for measuring topics in declassified documents, while the second is for measuring multilateral relations from country-to-country interaction data. Okay, so let's talk about declassified documents. As I'm sure you all know, the US government protects a massive amount of information under its security classification system. But what you might not know is exactly how much information we're talking about. For example, in 2014, over 64 million pages were reviewed for declassification, of which 27 million pages were then actually declassified. And these documents are super interesting to all kinds of people. For example, political scientists want to use them to understand government transparency. Historians want to use them to construct a richer narrative of the past. And journalists want to use them to find events that were never actually covered in the news. Amazingly, it's pretty easy for scholars to get access to these documents. For example, there are around 100,000 of them available on the Gale Declassified Documents reference system. And when I learned this, I got really excited, and I thought, wow, I bet there's a ton of interesting stuff I can find in there. For each document, there's a variety of different metadata, such as the issue date and the source institution, the classification level, and so on. And there's also the document text. And the text is especially useful because there's only so much we can learn from the metadata alone. For example, in 2007, the FBI released several previously classified documents on John Lennon. And from examining these documents' metadata, it would be totally reasonable to assume that they contain highly sensitive information. But in fact, as this quote indicates, this was not the case. The file contains little, if any, new information about Lenin, though it does present some bizarre details, like a description of an anti-war activist trying to train a parrot to speak profanities. Yeah, as I said, there's some interesting stuff in there. More importantly, though, it's the text that caused these documents to be classified in the first place. Therefore, many of the questions that are most interesting to social scientists involve the document's content. For example, are documents about race relations more likely to have a higher classification level if they also talk about police violence? Do documents about nuclear weapons have longer classification durations than documents about UFO sightings? So to answer these questions, then, we need some way of taking hundreds and thousands of documents containing millions of words and automatically extracting the most salient information to yield something that looks much more like this. So the two boxes on the left of this slide are topics that occur frequently in documents issued by NASA. And as you can see, they're all kind of about space. While the two boxes on the right are documents that occur topics that occur frequently in documents issued by the Atomic Energy Commission. And they're all kind of about nuclear power and nuclear testing and stuff like that. So the question then is, how do we uncover or measure topics like this? Well, we can represent a collection of documents as a D by V matrix of document word counts, where D is the total number of documents in the collection, and V is the number of distinct words in those documents. So a single element in this matrix, then, is the number of times the corresponding word has occurred in the corresponding document. So this is a toy example involving 6 documents and 6 words, though for real document collections, there are usually many more words than there are documents. Also, I've stemmed the words in this example. So for example, the column labeled Scien includes counts for science, scientific, and scientist. And if you squint, you can see that there are kind of two blocks in this matrix, one in the top left and one in the bottom right. And these blocks correspond to groups of words that tend to co-occur together in documents. So in the top left, we have CSS, social, Scien, and compute, while in the bottom right, we have Scien, compute, Python, and SciPy. And we can think of each of these kind of groups of words as representing a particular topic. In fact, we can uncover this topic structure by decomposing our count matrix, so remember it's a D by V matrix, into a D by K matrix and a K by V matrix, where K is the number of topics that we expect to find. So in this case, 2. The K by V matrix represents how prevalent each word is in each topic. There's an element for every topic word pair, so every word occurs in every topic, or is associated with every topic, but by different amounts. For example, the word social is the most prevalent word in topic 1, but less prevalent in topic 2. Most importantly, the top words, so the most prevalent words for a topic, provide a kind of a characteristic signature for what that topic is about. Similarly, the D by K matrix represents how prevalent each topic is in each document. And I want to note that a single document can be about multiple topics. So, for example, this document, which I spent a while constructing, is about both topic 1 and topic 2. I do computational social science, CSS, with both computer scientists and social scientists. Right now, though, I am at SciPy, which is all about scientific computing in Python. And I've colored the content words according to the topic that they're most strongly associated with, and I've left the stop words, so all of the other words that don't really have any content, which we'd usually discard before even forming our document word matrix, in gray. So how do we decompose our count matrix into these document topic and topic word matrices? Well, we specify a probabilistic generative process involving all 3 matrices by which our count matrix could theoretically have been generated. And then we invert this process using a statistical inference algorithm to recover the document topic and topic word matrices. And specifically for that generative process, we assume that each element in our count matrix, so each individual document word count, was drawn from a Poisson distribution, whose parameter is the corresponding element in the matrix obtained by taking the product of the document topic matrix and the topic word matrix. Just as a reminder, the Poisson is a discrete distribution over the non-negative integers, so it's much more appropriate for modeling count data than something like a Gaussian. It has a single parameter, its mean, so the generative process on that previous slide basically says, on average, our count matrix should look like the product of that document topic and topic word matrices. In the interest of time, I'm not going to talk about inverting the generative process using a statistical inference algorithm. There are a bunch of different ones out there, but I do want to note that the code can be really simple. So in this case, it's about 10 lines of Python, and that recovers those 2 matrices from one of those document word matrices. I'm also not going to talk about validating that the uncovered matrices do a good job of measuring topics. I will note, though, that social scientists typically assess 6 different types of construct validity, which correspond roughly to the 5 questions on this slide. And if you want to learn more about these questions, there's a video of my ICML 2015 tutorial on videolectures.net in which I talk in detail about how to validate measurements of theoretical constructs. So what I am going to do, though, is I'm going to show you some of the topics inferred from the documents in the Gale Declassified Documents reference system. So here are the 6 most prevalent words for 4 randomly selected topics out of 1,000 total topics. The first one corresponds to the Korean War. The second and third correspond to Vietnam War casualties and the Sino-Soviet split, respectively. While the fourth topic is about nuclear proliferation safeguards. So this starts to give you a sense of the kind of topics that are actually being discussed in this document collection. The top words in this topic are church, Catholic, Pope, Vatican, religious, and bishop. And I was kind of intrigued by this topic, and I couldn't figure out why the government would want to classify documents on Catholicism. So I plotted the average proportion of documents that are about this topic issued each year. And as you can see, there's a really big spike around 1942. And it turns out that's because 1942 was the year that Pope Pius XII gave his Christmas address about the Holocaust. Who knew? This topic is all about national conscription. And sure enough, there's a big spike in the proportion of documents issued around 1969, the time of the first draft lottery for the Vietnam War. There's also a big spike in the proportion of documents declassified around 2003, when the Iraq War appeared imminent. And I thought this was kind of interesting. And finally, this plot reveals the topics that are kind of over or underrepresented in documents issued by the FBI compared to documents issued by other institutions. And the 2 most overrepresented topics here, so the highest on the y-axis, are about race relations in Chicago and race relations in Mississippi. So before I move on to measuring multilateral relations, I want to note that there are a whole bunch of different topic modeling toolkits that you can use to do this kind of analysis yourself. For example, GenSim provides all kinds of topic modeling functionality in Python. And there's actually a GenSim sprint tomorrow, I think. There's also an implementation of one of these statistical topic models in scikit-learn, though I haven't used it yet, but there is a scikit-learn sprint as well. So you can go to either one of these and sort of find out more about how to use these models. And there's also a bunch of relevant Python code on my GitHub. Okay, so let's talk about measuring multilateral relations. Over the next few slides, I'm going to tell you about a model that takes a bunch of country-to-country interaction data and learns some underlying latent structure that connects these interactions. And as you'll see, this model is pretty similar to the model I just told you about, but because it's applied to a really different type of data, we can use it to measure a very different type of construct. So the starting point for this work is the idea that international relations are inherently multilateral or networked in nature. Specifically, the behavior of countries or pairs of countries is highly dependent on the network that they're embedded in. And so as a result, we can't study country-to-country interactions in isolation. We have to study them as part of their broader context. For decades, political scientists have studied relationships between countries by collecting and analyzing pairwise event data that looks like this. So each row on this slide corresponds to a single event, and each event is characterized by 4 pieces of information: a time step within which that event took place, a source or sender country, a target or recipient country, and an action type. And these action types come from some ontology. So here, for example, they're from the Weiss code. So where do these events come from? Well, for many years, political scientists manually extracted them from news articles. So for example, the last event here, 900731 IRQ KUW mobilization, was manually extracted from this headline here. July 31st, 1990, Iraq increases troop levels on Kuwait border. Having curated a database of events like this, political scientists can then sift through the events and figure out coherent threads or meaningful narratives involving particular sender countries, receiver countries, action types, and time steps. And these narratives, or multilateral relations, are latent representations of who did what to whom when. As a result, they can be used to study coalitions, treaties, cartels, alliances, and so on. So, for example, the events on this slide actually correspond to the Iraq-Kuwait crisis. Iraq is the only sender here. The receivers are Kuwait and Egypt, and all the actions are pretty aggressive. But here's the thing, human-curated databases like this are very time-consuming to construct. And so, as a result, they're generally very small and specific to certain regions or certain action types and things like that. Because of this, there have been several efforts over the last few years to automate the event extraction process using modern machine learning and natural language processing tools. And this is great. It means that political scientists can study events extracted from millions of news articles from all around the world. But the net result is not something that looks like that neat table on the previous slide. Instead, it looks more like this kind of giant hairball mess. Unsurprisingly, these events are super noisy, and there are far too many of them for any single human to sit down and read and analyze manually. So to make these data sets useful for political scientists or historians or journalists or media scholars, we need some way of taking millions of noisy pairwise events and automatically teasing apart the coherent stories or meaningful narratives to yield things that look more like this. So this is a multilateral relation discovered by our model. It's characterized by time steps in the top row, senders in the bottom left, receivers in the bottom middle, and action types in the bottom right. And if you look at the time steps, you see there's a big spike around 2001. If you look at the senders and receivers, you see the main senders are Afghanistan, Pakistan, and the US, while the main receiver is Afghanistan. This is the Afghanistan war. It spikes right after 9/11, then it drops down, and then climbs back up over time. So how do we discover multilateral relations like this from these millions or billions of pairwise noisy events? Well, one way to represent an event dataset is to count the number of events of each distinct IJAT event type. And by aggregating the events in this way, we end up with a 4-mode event count tensor, whose modes are senders, receivers, action types, and time steps. And each element of this tensor is a single count. Since I can't draw a 4-dimensional hyperrectangle, I've drawn a 3-mode tensor here, so a 3-dimensional rectangle or hyperrectangle whose modes are senders, receivers, and action types. And this is what we'd get if we ignored time steps and counted the number of events of each IJA event type. All right, so we have this 4-mode tensor, but what are we going to do with it? Well, we can decompose it into 4 factor matrices and then show that the factors correspond to these multilateral relations. But rather than leap right into tensor decomposition, I'm going to start with matrix decomposition and build it up from there because it's simpler, and this will also connect the model to the one I just told you about. All right, so imagine that rather than having an event count tensor, we have an event count matrix. Specifically, we're going to forget about action types and time steps, and just imagine that we have an n by n sender-receiver matrix, where n is the total number of distinct countries in our data set. And a single element, ij, in this matrix is the number of times country I took any action toward country j at any point in time. So this is a toy example involving 6 countries. And again, if you squint, you can see that there are 2 blocks in this matrix, one in the top left and one in the bottom right, just like there were in our document word matrix previously. But now we can think of these blocks as communities of countries who interact with each other. Like the previous model, we can uncover this community structure by decomposing our count matrix into two factor matrices. One of these, the sender factor matrix, represents how active each country is as a sender in each community, while the other one, the receiver factor matrix, represents how active each country is as a receiver in each community. Together, the sender and receiver factors for a single community, so for example, community 1, as I've depicted here on this slide, provide a kind of a characteristic signature for that community, specifically who the top senders and receivers are. Again, we can uncover these factor matrices by specifying a probabilistic generative process by which our count matrix could theoretically have been generated, and then inverting this process. The generative process here is super similar to the one from the previous model. Specifically, we assume that each element in our count matrix was drawn from a Poisson distribution whose rate parameter is the corresponding element in the matrix obtained by taking the product of our sender and receiver factor matrices. So same kind of thing, we're just looking at some different matrices here. So what happens then when we move back to the world of tensors? Just as a reminder, our goal is to take a 4-mode tensor, whose modes are senders, receivers, action types, and time steps, and decompose it into 4 factor matrices that correspond to multilateral relations. Well, it turns out we don't actually need to change very much. All we need to do is introduce 2 additional factor matrices. One for action types, and one for time steps. Then we just assume that each element in our count tensor was drawn from a Poisson distribution whose rate parameter is the corresponding element in the 4-mode tensor formed by taking the tensor product, so rather than a matrix product, we're taking a tensor product now of the 4 factor matrices. And that's it. Of course, the 2 additional factor matrices mean that we're no longer discovering simple communities of senders and receivers. And because a single sort of K value now indexes factors from the action type and time step factor matrices, as well as the sender and receiver factor matrices, we're instead discovering multilateral relations that characterize who did what to whom when. I'm not going to talk about inverting the generative process, but we do have code for statistical inference up on GitHub, and the inference algorithm is pretty similar to that of the previous model. So here's a multilateral relation discovered by our model using the IQs dataset spanning 1995 to 2012 with monthly time steps. The time step factors are in the top row, while the factors for the top senders, receivers, and action types are in the bottom row from left to right. If you look at the time steps, you see there are 3 spikes here, one around 1999, one around 2001, and one around 2008. And the top 3 senders and receivers are Serbia, Albania, and Kosovo. So what is this? Well, it's the Yugoslav wars. The first spike is the Kosovo War. The second spike is the Macedonian insurgency. And the third spike is Kosovo's declaration of independence. So as a side note, I do want to point out that we found it was pretty easy, even for non-experts, to interpret the multilateral relations discovered by our model. If you Bing for the top senders, receivers, and time steps, there's usually a Wikipedia article among the top hits that explains what's going on. All right, so here's another example. This multilateral relation was discovered by our model using the GDELT dataset spanning 2011 to 2012 with weekly time steps. And there are 2 spikes here, one in June 2012 and one in September 2012. The top senders and receivers are Ecuador, the UK, the US, Sweden, and Australia. Does anyone know what this is? WikiLeaks, Julian Assange. Same kind of thing. So yeah, this one is all about Julian Assange, the founder of WikiLeaks. He's an Australian national who is under investigation by the US and Sweden for various crimes. Then in June 2012, when facing extradition to Sweden, he sought asylum at the Ecuadorian embassy in the UK, which he was then granted in September 2012, that second spike. So, as these examples illustrate, the multilateral relations discovered by our model really do correspond to meaningful narratives involving particular senders, receivers, action types, and time steps. And we can use these measurements then in other explanatory models down the line. But because the model itself is very similar to the one we use to measure topics in declassified documents, I hope this also emphasizes that Poisson tensor decomposition is a super general framework for measuring all kinds of unobservable theoretical constructs from count data. Before I move on, I want to note that all our code is on my student Aaron's GitHub, and you can download the data that we used from the GDELT and IQ's websites, and we've also published a couple of papers on these kinds of models that you can read if you are feeling really enthusiastic. Okay, so for the last couple minutes, I want to take a step back and talk about working with social data, focusing on its implications for developing responsible and ethical technology. So as well as pursuing different research goals, computer scientists and social scientists typically work with very different types of data. Computer scientists work with large-scale digitized data sets that are often collected and made available for no particular purpose other than just machine learning research. In contrast, social scientists use data collected or curated in order to answer specific questions. And because this is labor-intensive, these data sets have traditionally been small-scale and often non-digitized. But, and this is kind of one of the driving forces behind computational social science, thanks to the internet, we now have all kinds of opportunities to obtain large-scale digitized data sets that document a variety of social phenomena, some of which we had no way of studying previously. For example, my colleague Bruce Damaris and I wanted to conduct a data-driven study of local government communication networks. So in other words, how political actors at the local level communicate with one another and with the public. Turns out most US states have sunshine laws that mimic the Federal Freedom of Information Act. And these laws require local governments to archive textual records, including, in many states, email, and disclose them to the public upon request. So Bruce and I therefore issued public records requests to the 100 county governments in North Carolina, requesting all non-private emails sent and received by each county's department managers during a randomly selected 3-month time frame. Because Bruce is a social scientist, we also decided to use the process of requesting these emails as an opportunity to conduct a randomized field experiment to test whether local governments are more likely to fulfill public records requests when they're aware that their peers have already fulfilled the same request. I'm not going to talk about the details of our experimental design, but on average, we found that counties who were informed via this treatment message on the screen that their peers had already complied took fewer days to acknowledge our request and were more likely to actually fulfill it. And now we have 500,000 emails from 23 different counties, and it's not the Enron data set. Yay! Okay, so this is great, right? We have all these opportunities, but it would be super remiss of me not to point out that these kinds of new opportunities also raise new challenges. Most conspicuously, it's really tempting to say, well, why not use these large-scale social data sets in combination with the powerful predictive models developed by computer scientists? But here's the thing, unlike the data sets traditionally used by computer scientists, these new data sets are often about real people. So their attributes, their actions, and their interactions, going about their everyday lives. Not only do these data sets document social phenomena on a massive scale, they do so at the granularity of individual people and their second-to-second behavior. As a result, they raise some really complicated ethical questions regarding privacy, fairness, accountability, and transparency. It's really clear from the media that one of the things that terrifies people the most about machine learning is the use of black box predictive models in social contexts where it's possible to do more harm than good. There's a great deal of concern, and rightly so, that these models will reinforce existing biases and marginalize certain populations. In addition, when data points are humans, error analysis takes on a whole new level of importance. It's not enough for a model to be 95% accurate. We also need to know who's affected when there's a mistake and in exactly what way. So when we use machine learning to reason about social phenomena, and especially when we do so to actually draw actionable conclusions, we have to be exceptionally careful, more so than when we use machine learning in other contexts. But here's the thing, these ethical challenges aren't entirely new. Yes, they might be new to computer scientists, but they're not new to social scientists. To me, then, this highlights a really important path forward. Yes, machine learning is useful, and to be honest, I'd be out of a job if I didn't think that. And in particular, I think it can be really useful for social science. But we have to treat machine learning for social science very differently from the way that we treat machine learning for, say, handwriting recognition or playing chess. We need to prioritize interpretability so we understand what's happening. We need to prioritize error analyses so we know who is affected when there are mistakes. And we need to represent uncertainty so we know when our model really isn't confident about the kinds of predictions and conclusions it's making. And more importantly, most importantly, we need to listen to social scientists in order to understand the ethical implications and consequences of our modeling decisions. So before I stop, I want to note that there are many ways to learn more about these issues. There are a whole bunch of essays, reports, and academic papers online. Most relevant to this conference, some researchers at Columbia University recently developed the FAIR Test toolkit for finding unwarranted assumptions in data-driven applications. And they've actually integrated it into the SciPy evaluation framework. And with that, I am going to stop. Thank you. Sure. No, obviously.
Do the microphones back there?
I'm just going to stand here awkwardly.
I'll let you pick and I'll just go.
Oh, okay, you.
Were there any surprises you found that you just weren't expecting when you were mining for international events?
Oh, so actually, that's a really good question. We are still wading through everything that we found. We were, to be perfectly honest, we were pretty surprised to find that Julian Assange multilateral relation. We were expecting to find sort of wars, maybe alliances, that kind of thing, but we hadn't realized that when you run these kinds of models on data sets at that granularity, you actually get these super fine-grained things like that. So for us, that was probably the most surprising thing that we found. We are still going through all of these, and I think actually on my student Aaron's GitHub, we have maybe 100 or maybe 200, I can't remember, of these multilateral relations, so people can kind of dig through them and look at them themselves.
Questions?
Yep.
Do you think it will be possible to share this data like as widely, these private data sets, so that machine learning researchers can work with them do you think all machine learning researchers need to be educated first on how to use the data, or do you think it's possible to anonymize it in a way that maybe this issue go away to some part? Or
Yeah.
how do we do this?
This is a really good question. Okay, so first of all, I will point out that anybody with access to the Gale Declassified Documents repository can get access to that. Anybody can download GDELT and IQs. The question really comes when we're talking about these other data sets, like, for example, the email data that Bruce and I gathered. And this is where it gets tricky. When we started this process, I thought to myself, it's public record data. You know, anybody can request this. It can be made available to the public. I'll just gather this data and I'll put it online for everybody to use. And yay, we'll have another data set that isn't Enron. But it turns out that county governments are supposed to apply all kinds of security and confidentiality exemptions before providing the data to us. And they didn't always do that. So there's things like people's social security numbers in there. There's private information about people's personal lives in there because people use email for things other than just work. And then the real question becomes what to do. So technically, this is public data. Totally fine for anybody to get it. Thus, legally, it would probably be fine to just stick it online. But that's not the same as being ethical. And often being ethical is sort of more difficult than just fulfilling that legal obligation. And so we are not sure what to do about this. We haven't made the data available because we're not sure it's ethically okay to do so. Yes, it's public data, but is making it more accessible to people all right? Well, I don't think it necessarily is. The first time that I think a lot of machine learning researchers ran into this question was when the WikiLeaks data became available. And so a lot of people wanted to actually start analyzing all of these documents and see what they could find. But it quickly became apparent that there were people's names and addresses and all kinds of other information in there. And also became apparent that making this information much more available so people knew who those people were was not okay. So I think these are the kinds of questions we have to wrestle with. I really do think that it's really important to educate people about this stuff. I find it surprising that in this day and age, given the number of people working with social data, that computer scientists, for the most part, do not get training in things like ethics, fairness, bias, accountability, all of these topics. We are beginning to see some of this change, but it is still moving quite slowly. I do think it's really, really important. We're very used to, certainly old school machine learning researchers, we're very used to thinking of data points as data points, whatever, it doesn't really matter. But when we are dealing with social data, there are people behind those data points, and so we do have to go that one step further. Yeah.
So in your tensor decomposition, you're treating each week independently to some extent, it seems. How do you use the cross-temporal connections to identify the total event structure as opposed to...
Yeah. So I think your question is about the fact that we are treating time steps as being independent. Thus, we could theoretically reorder the time steps and the model wouldn't care. Wouldn't really matter. We're not taking advantage of the fact that there is significant temporal structure. What happens in one week is not unrelated to what happens in the next week. Well, we just submitted a paper to NIPS on dealing with this. It is under review at the moment, and maybe it'll get in. I don't know. If it does, then I will tell you all about it. Yeah. But yeah, that's a great question. It was something we really wrestled with. The tricky thing there, I do want to point this out, the tricky thing there is that if you look at the data itself, it's actually really spiky. And so if you try and do some kind of temporal dynamics on the observations themselves, it doesn't work very well because there's so much squiggling around. What you actually need to do is put those temporal dynamics on that kind of latent structure instead, and so deal with it that way. But anyway, details, whatevs. Yeah.
Let's take one more.
When you were looking at declassified data and determining relationships, did you ever get a hold of any security classification guides that would explicitly tell you many of those relationships?
Okay, so yeah. So the question is, when we were analyzing declassified documents, Did we get hold of any security classification guides that kind of explained some of these relationships and gave some of this broader context? So the simple answer to this is we've done a lot of reading on government transparency and about also the historical events that were kind of happening and taking place. There is some amount of information out there surrounding sort of these document collections as a whole. We looked at some of this to sort of understand that broader context. I don't know if we sort of dug into super nuanced details to see if there were specifics in those documents that we could then find evidence supporting it within the data sets themselves. But I think it would be really interesting to do that kind of thing, I guess. Yeah.
Thank you all for all the questions. Let's thank the speaker.